The next speaker does not need any introduction. Anton is up with the SDR transponder for AfriCube. Once have we said anything about AfriCube? Not a word.
Not a word yet.
Yeah, we're talking about AfriCube and nobody knows what it is, who it is.
Well, we've said enough on the web already.
I'll leave that to you. Okay, Anton, you're next. Most interesting, we come up with these names, but you'll find out rather sooner than later on what that is all about.
Okay, right. Yes. Hello? Right. Okay, so I was sort of following the Klets Coast project closely, and I think about a year ago I was asked to sort of look into a possible SDR version satellite for following Klets Coast. And we started a project called AfriCube, and we sort of took the specifications of what you want to do. It's basically a sort of a mirror transponder telemetry. For now, that's the specifications we've got. A 1K, one U cube, and we started the project. So what is the project about, and what do we need to build? I think the thinking was that we will probably use the CP of the power supply unit of Klets Coast, and then maybe the antenna deployment of Klets Coast, the frame of Klets Coast, but we replace the transmitter and receiver and the transponder with SDR. So the idea at this stage is we want to look at RX band. This is basically the components that we need to develop. We need to do RX blind pass filter. We need to have at least a 12-bit SDR receiver. And at this stage we're looking at the MSI chipset. Processor, at this stage we're looking at STM ARM type processor to do the SDR and possibly the telemetry and household onboard services. For now, we're looking at the local oscillator for the SDR mixes and so on as a SI570. It's I2C controllable, so we can change the frequencies if we have to, calibrate it. Transmitter, we're looking at IQ modulator TRF3701. This might be discontinued shortly, but there's a newer version. I think it's the 2 or the 3, which has got similar footprint, and it can go actually higher. This one I think can only go up to 1.2 gigs, with a new one I think can go to 3 gigs. So it will even give us opportunity maybe to look at S and L bands. We get power amp stage. At this stage we're looking at the MMZ09, which is about a 30 dB power amp stage. We're going to get out of this unit about 0 dB, and we need 27 to transmit down to earth. That's our estimated power. So this should give us enough power.
On what frequency?
It's 2 meter up and 70 down. Or we can, this configuration, we can probably possibly do both, but we'll probably only build the filters for one or the other. But it's all configurable, but the hard-coded part will be the filters. Power supply, the design at the moment is we're purely looking at 5 volt. The whole system will operate 5 volt only. Ideally, we would have liked to run on 3.3 because that would reduce power usage. But the power amp stages and some of the RF stages, we at least need 5 volts. So that's simplifying the power supply a little bit, but might cause us to use a little bit more power than we should. The estimated power budget, total usage, I think we've got a limit of 2.8 watt for full service. And obviously we need to try and reduce that. I think the betas that we're testing at the moment, we probably can run on 2.5. But we will see this as the test could carry on. Standby and telemetry only modes will obviously reduce this. So what we probably can do to reduce power, if there's no usage, we will switch off the transmitting side, only run maybe CW telemetry, just at least you can find it. The moment it gets an uplink, then it can switch modes automatically and maybe switch on the linear transponder automatically. So that's another way to save power. Space frame and antennas, like I said, we're trying to probably reuse what we've done on Kletsco's. So we started with the transmitting side because the receiving side is pretty easy. We can use a dongle for testing purposes now. But the transmitter side is not something we can just get off the shelf to get low power. You can get stuff off the shelf, but they're not really low power. They waste a lot of heat and they're quite expensive. My thinking was also, can we use a simple SDR chipset for RX and an IQ modulator board for TX. So for a transponder point of view, we'll probably take the IQ feed coming from the SDR receiver, resample it to a higher frequency, apply some filtering, then mix it with the telemetry data that we will simulate with generating audio to IQ, mix it to IQ signals, and then we'll transmit the combined signal on the transponder output. So there won't be a separate transmitter for telemetry. It's all on the same bandwidth and the same SDR transmitter. We will just mix our two IQs. For testing at the moment, we're using an Orange Pi. That's the footprint we've built. It's very small. It's about this big, the transmitter. We've got some issues with it at the moment. Why the Orange Pi? The Orange Pi is fast. It's pretty powerful. Small, low power usage. It's not that low. I think if we run pure STM processes, we probably can reduce it to more than half. So I think we probably, when we do the final board, we'll move processes and so on. But for now, for testing and getting it up, we're trying to use commercial stuff. That's why we're using the Orange Pi. This is the IQ modulator board we've developed. At the moment, in theory, it should be able to give us 1 watt. 500 milliwatt maybe is something that we can transmit, but I think because of the power budget limits, we'll probably run at 100 to 200 milliwatts normal operation. So it's a little bit over design, but at least it will not get too hot and we won't run it to its limits. Proper output, low pass filters, we need 40 dBs on second harmonic, so that's 7-stage normal conventional components. That is a section here. And it goes out. There's I think this is the power amp stage. This is the IQ modulator. And here sits the local oscillator. So that's the whole TX. And if you look at the size, it's a very small footprint. It's almost half a cube size. Narrow to 100 kHz bandwidth. We're probably not going to run 100 kHz because of the power limits. We're probably going to run closer to 20 kHz. But I mean, we can probably run to 100 kHz if we had enough power. Any modulations, we can probably add anything we want by using the IQ modulators to mix it in on the output. So we can, if we can have enough space, we can maybe put a small camera on there. AFSK for telemetry, PSK possibly. SSB I don't think we'll use. AM, FM, maybe FM we'll use. So we can use any modulation with this. Or raw IQ would be the mixed telemetry data. It should be low power potential to be used in the balloon flights as well. So the thinking was that this module, because we're doing the prototype for it, and if it works well, we can probably reuse the prototype for balloon environments as well. That could be used for that. There's reuse for the prototypes. Thinking was also to use the MSI SDR as a chipset for reception. I think I've told you that. The system should also be suitable to be used for ground stations. So the thinking was that we can probably reuse this on Orange Pi as a ground station, as a transmitter. Possibly we can use this for SL if we use the other chip, the one that can go higher to 3 gigs. Then if we replace the modulator chip with the newer version, we can probably use it for SL as well. What else? The modulation input must be from a standard Linux AMSAT driver. So the thinking was at the moment to get the prototype going, all the standard SDR software is using ALSA as the audio drivers, so we can feed the IQ straight. The Orange Pi fits 100% underneath this. This is the standard Raspberry Pi connector, and then the Orange Pi has got this additional connector which is called audio in and audio out. So it's a perfect fit. We don't need any other connections to it. It plugs straight onto the Orange Pi. The local oscillator can be configured, the modulation audio I2C controller, the local oscillator, which is that chip there, and other pins which is controlling the I2C is coming from there. At the moment we were testing it with the GNU radio blocks. From a prototyping point of view, I've tested this with Lime SDR using the GNU radio blocks to test the concept from a software point of view. That works reasonably well. The next step is to move it onto this and get this working with the GNU radio blocks. We then, from that point, once we've proved the concept, we're going to move it to C and Python. The final libraries will be C and Python, which will then do all the control for the final satellite. This is a commercial SDR front end, which is the MSI chipset. You can buy this off the shelf, but we want to probably implement the same configuration for the reception port. And you can see it's a normal size capability, and we will obviously add some additional filtering on the front end, some soft filters for the final satellite. That's sort of the high-level block diagram. The thinking was that we have these, the bandwidth in, we will have control on the side and telemetry on the side there. We have the front end, which is the MSI. This is the SDR blocks. There's a project called CSDR, as you can see there. It's an open source project, so the thinking is to use Python and C libraries to get the input from the MSI chipset, read it in, manipulate the low-pass filters, remap it to higher frequency clocks, apply software AGC to it, then put it in a mixer, and then to the modulator board, the board that I've just shown you. So that's sort of the thinking. So this part here is all software, and that part is the RF in to IQ, and this is IQ to RF. That will be the principle of how it should work. Then we will have other applications inside the unit. We will have a CW generator, which is normal C, standard C libraries that you will use. This is tested on a balloon already. This part we've tested a year ago, and APRS, we've tested this on a balloon a year ago. So we'll reuse this. We know it's proven it's working. That will be mixed into the IQ signal, and that will be transmitted on the side, right at the edge there. Then we've got the actual CPU unit here, and the only purpose of it is to go and read the battery voltage, the sensors, manipulate the power supply if possible, maybe switch modes. We're probably going to have 3 to 4 modes, a standby mode, standby with CW, and then a standby with APRS, and then a full functional linear transponder with beacon. That's sort of the modes that it will operate. this part we still need to build and think how we're going to do it. The power supply unit already used in Kletsco's has already got some of the sensors on it, so we will reuse that part. But I think the other ones, the solar part, we will have to add, and the battery already exists. So some of these already exist. We will reuse the Kletsco's units for that. So this is the transmitting data flow. I have the orange part at the moment connected on the left, which has an additional USB. So audio, audio and output ports not normally available on a normal Raspberry Pi. That's why we selected it. It's also a small footprint. I think I've told you that. I told you we're using the local oscillator. I told you we're getting a 0 dB output and we need a power amp stage. We're going to amplify to 500. At the moment we can operate in only any of those frequencies. 145, 43 and 1.2 gig. If we use the new chip we can probably go up to 3 gigs. This is the power amp chip, and that's basically the principle of the transmitter board. This is the diagram of a transmitter board. So we've basically got the normal standard Raspberry Pi interface. We've got the local oscillator. We've got the A to D converter here. This A to D converter reads the output power. Do you think it's somewhere there, that point there? So this amplifier stage has got an output power detector built into it. So we're going to read the output power back, and then we can adjust the modulation scheme of the IQ, so we can actually monitor our output power and modulation. So we got a full feedback onto that through the A to D. This is the modulator that will get the audio I and Q signals from the Raspberry Pi. That output will go to the power amp stage, and there's the output filter. So it's reasonably simple, straightforward. That's the software. So I think I just elaborated. So this is the library. You can have the feed coming in, we can have the library, remap it to 100 kilohertz bandwidth, use some filters to it, and then mix it all the way out. And this is the telemetry part. So the plan is to use PSK, and I think we've actually made the change. Yesterday we had a meeting and we've decided we're not going to use PSK, we're going to use AFSK. And the main reason for that is that schools and school kids can easier decode AFSK than FSK, so we're thinking of changing that. So that's already changed. And then the CW, at this stage we're thinking of 10 words per minute for the beacon. That's about that. Software steps. So from the STR we'll get about 720 kilohertz in, and we will resample it to 100 kilohertz. Low pass filter, software block, telemetry audio, IQ, off file sent to also audio device. And that's it. That's the step from in to out from a transponder point of view. Then create a CW audio from a CW application that's already existing that we've tested. This could be reused on the balloons as well. Then convert the CW into audio or PSK and get mixed in the IQ. That's the second block we have to do. Create AX25 message from Direwolf. So we'll use a Direwolf application there for the moment. We'll probably use some Python application which is written, which will be dedicated for application in the future. We will also send the temperature, inside, outside, battery voltage and everything with the telemetry. We probably might send CWs some values as well, but maybe just the battery voltage on the CW. We will have a cron running in the background for now. Every 3 minutes it will send a CW message just as a beacon to save power. This can be changed to 1 minute and scripts to monitor automatic level on the transmitter side, so it will adjust the transmitter output level and the TX output level. So that will run in the background independent from the normal operations. Then there's just creating startup scripts to start the transponder and telemetry audio. When it as a reset, if we have a reset on air, so it will automatically start up. read the RF power, and by reading the I2C and the A to D converter, I've showed you that, just IQ levels, depending on the output levels. So it's a little bit of repetition. I've got for testing purpose, to test the software that we've done, I've just got a laptop here at the moment with the Lime SDR, just to test the concept if these software blocks will work, and I've got it actually on at the moment on my desk. I've got you guys that want to listen, or it's got a technology, you can listen to it, but I've got it in concept, we've got it tested. 0 is 6 alpha in the Charlie testing 1, 2, 3. I think it's over-modulating a bit. But in concept, this is going through the transponder at the moment. It's a little Lime SDR sitting on my table with an orange pi. It fits in a 1 cube as it stands here at the moment. So in principle, this should work. As now, we just need to do the modulator board and the RX board, and we should be there. This is just a video of basically what I've demonstrated to you now. I don't know if it will play. Let's see.
If you don't load it, if it's on your stick, it won't. You want audio?
Yeah.
Because we've plugged it out. Is it running?
No, it's this is Anton Janowski, Zulu Romeo 6 Alpha and Charlie. I'm just taking a video to sort of demonstrate how a linear transponder works with a small little Lime SDR Mini SDR in full duplex mode, and I'm going to use 2 Baofengs and to transmit, and then I'll shift the frequency a couple of channels up and down, and basically what you will see is on the VHF is where I'll transmit, and you'll see them both, they are VHF, and then on the UHF side here at the bottom you will see the output of the transponder, and I'll increase the frequency here, and you'll see the frequency will linearly jump up and down on this frequency at the bottom. So basically what I'm going to do is just I've got 2 Baofengs. The one is set on 145/300, which will be my starting transmitting frequency, and then I've got the other Baofeng, which will be on 435/500, and it will be listening there, but it only works for the first frequency, and thereafter, as I'm jumping up and down, you will just see it jumping on frequency here. So the first one is just there to verify the transmission. So I'm going to do the first transmission now using the Baofeng. 006 Alpha in Charlie is testing the linear transponder. 006 Alpha in Charlie is testing 1, 2, 3. So you will see the carrier in the second waterfall, just on 145/300, as you can see there, and there is the output of the transponder. So what I'll do is I'll up the frequency with 5 kHz, and you should see the jump in the actual transponder output as well. 06 IC testing 1, 2, 3. Zulu Romeo 6 Alpha and Charlie testing 1, 2, 3. There you can see the frequencies jump upwards, and I'll take it another channel up, and you'll see it jumps again. So you'll see now the frequency here is now spot on 300, and if I take it up, you'll see it will eventually go past 145/300. Now I'm transmitting again. You'll see the frequency on the input has jumped a little bit up there, and if I go to the bottom, it's jumped quite a bit.
I take it another frequency up, and there it's jumped again. And I take it another one, there it's jumped again. I've taken it 3 down, now you can see it jumped quite a bit down. So that's sort of...
Yeah. So that's just sort of a quick explanation of how it will work. The lines of code to make this work was probably not more than 30 lines of code to make this work on the line STR. So from a technology point of view, it's actually quite easy to do this. It's now just the filtering and the mixing of the telemetry part that we need to add and make it work. So from a principle point of view, it sounds reasonably easy, but we'll probably find some tweaks and things that we have to sort out to make this work properly. I hope this was informative. Let's see if I've got something left. I think that was it. Yeah, that was it. Any questions? Okay, so there's 2 stages of filtering. Obviously on the front end coming in, we need to, the SDR front end is not so selective from a reception point of view, so we'll probably have a SAW filter in the front to do some RF selective filtering, 100 kilohertz wide, something like that. We also do, when you're upsampling or downsampling IQ data, normally before you are upsampling, you have to filter out unnecessary data, because otherwise if it's upsampled, there's more noise. So in the actual IQ data stream, we will filter, bandpass filter on the actual 100 kilohertz that we're interested in. We'll upsample, we then apply some other filtering to it. We apply maybe the mixer, we apply whatever we need to do, and then we will downsample. So normally before we downsample, we won't filter it, but we will filter it after the downsample, because that will reduce, if we filter before, we actually adding additional delay on it. We will filter afterwards, because then we'll get rid of the last harmonics on it, and then it's on the way out. And then obviously we need second harmonic filter on the output, as I showed on the RF side. So there's going to be about 2 filter stages in the IQ, in the software, and then a front-end filter and an RF filter on the way out. Any other questions? Okay, great stuff.